Hello everybody, it's Mr. Arocena, and on today's video we're going to be talking about applications of electromagnets. So, this video is basically kind of an information dump about some of the simple applications and some of the more futuristic, exciting applications of electromagnets. So the first one we'll talk about is the speaker. So the speaker is an electromagnet, and what it does is it takes advantage of the fact that you can easily control the strength of an electromagnet, and you can also easily control the direction that the magnetic field goes in. And it does this by varying the electric current. Now when the electric current changes, so as we change the electric current, it will create a change in the magnetic field. And what that does is it then creates, or it causes, so the varying magnetic field will cause the speaker membrane to vibrate. So when a speaker generates noise, what the speaker is doing is it is altering the electrical signal ever so slightly, several times per second, which will cause the magnetic field in here to constantly change, and that constantly changing magnetic field will cause the speaker cone to constantly vibrate, and that will generate sound. Okay. And it does this because, yeah, again, electromagnets, you can control the strength, direction, and control the strength and direction of the magnetic field relatively easily because all you have to do is alter a current. Another application that's kind of simple is the electric bell. So this is what you would find, say, like in a school fire bell or an emergency bell of some variety. What happens here is that you have this switch point, which is here. So there's my switch point there. And when a current passes through the coil of wires, it turns this electromagnet on. So this electromagnet gets turned on and will attract the bell, or not the bell, it'll attract the striker to the magnet, and that'll cause the striker to hit the bell. Now when it does that, the contact point is broken, so the current stops, and then the striker will reset, close the circuit again, which will turn the electromagnet on. The striker moves this way, hits the bell, circuit stops, magnet turns off, and this repeats until the power source of the electric bell is turned off. So this is kind of a neat way that you can use a controllable magnet to do some simple task. Right, so there's a couple of kind of mundane applications of electromagnets. Now the next application, this one's kind of more futuristic, and it has some application. This is what's called the Coilgun. Sometimes it's called a railgun in certain science fiction settings, but the idea is basically the same. You basically have several electromagnets, and you use the electromagnets in quick succession to accelerate a magnetic object. Sometimes this is called a Gauss rifle or a Gaussian cannon. And the idea is that you turn one magnet on to attract the object. So as you can see, the projectile is moving this way. So it's being attracted by this magnet. Then as the projectile passes through and it gets at somewhere on the second half of this magnet, the current flow is reversed, so it'll repel the object, and then the second magnet is turned on to continue attracting the object. And then same thing, once this projectile gets to the second half of this magnet gets reversed, this magnet gets turned on, and the process continues. Depending on the number of electromagnets and how long this path is, you can actually accelerate objects to quite dizzying speeds. We use this on a smaller scale to accelerate charged particles. So any kind of particle accelerator uses a very similar principle to accelerate charged particles through the accelerator. And then we can accelerate small subatomic particles to within, I think, 99% the speed of light. And then we crash them into each other to see what happens. That's usually what we do with particle accelerators. All right. Now, in order for to get the best coil guns or the best particle accelerators, we often take advantage of superconductors. Superconductors are just conductors with zero resistance, like not near zero, actually zero resistance. So when metals get to near absolute zero, a lot of metals will exhibit superconducting behavior, where you have zero resistance and you can pass near infinite current through the superconductor. Now, the current is not infinite though, because as you pass current through the superconductor does heat up, and if the temperature is high, like if the temperature is high, then the superconductor does gain some resistance, but the resistance is still very, very low. Now, what superconductors allow us to do is it allows us to create really, really powerful magnets. Because if you recall, you can create magnetic fields using the equation B. Magnetic field is equal to mu naught Ni. So if the current is really, really high, then we can raise the magnetic field to really, really large amounts. Okay. And what's really neat about this is it can create some really cool situations. A physicist by the name of Meissner was playing around with these superconductors, and he noticed that if you have a superconductor, might be a little difficult to see here, but this is a magnet. So this is a magnet, one of those ceramic magnets, and it will create a magnetic field around itself. Now, interesting enough, when this magnetic field comes into contact with the superconductor, it will create a current within the superconductor. And because that current is really high, that current will then create its own magnetic field, which will repel this magnet. So what this in effect does is the magnet can actually levitate itself on top of a superconductor, because as the magnet kind of bobbles up and down, it creates a changing magnetic field, which then can create a current inside here, and that current can then create another magnetic field which opposes the magnetic field and then causes the magnet to sort of levitate. So that's the Meissner effect, and it's really neat because we've used this to create some really interesting things. Right. So yeah, so superconductors are really useful for creating superconducting electromagnets, and it's basically the same as a regular electromagnet. The only difference is that the coil is made of a superconducting material. This allows us to again generate large amounts of magnetic field because we can pass large amounts of current through that superconducting material. The three sort of main applications of superconductors are in particle accelerators, MRI devices, and in some places in the world, maglev trains. So the particle accelerator kind of operates in the same way as the coil gun, where that you have alternating magnetic fields and you can cause a particle to move really, really fast. And as the particle goes through the particle accelerator, the stronger and faster, or the stronger the magnetic field and the faster you change the magnetic field, it gives a particle more acceleration and greater energy. We can then use path of these to actually cause the particle to bend its path. So depending on the construction of our facility, we can either pass it going straight or we can bend it around. So if you recall from our visit to Triumph last year, for those of you who came with us, the Triumph accelerator is built as a circle, so the magnetic fields in that accelerator would be designed so that the particle moves in a circle. Okay. Now MRIs are another application of superconducting magnets, because what we can do with the superconducting magnets is we can generate magnetic fields on the order of about 1 Tesla or greater. This is important because what it does is it effectively causes all of our atoms to kind of align in a single direction. It doesn't actually hurt us too much, but we can then use other materials to cause some of our atoms to go in an opposite direction. Okay, and this is kind of partly why it's for anyone who's gone into an MRI, why piercings and other things like that tend to, you will have to take them off before going into an MRI, because having a magnetic field in the order of a Tesla can cause quite a lot of damage, or it'll attract almost any magnetic substance to it and not let go. Okay. Now, the very stable and uniform magnetic fields will then cause basically everything inside it to, again, magnetically align in a particular direction. And we can use the alignment of those particles to sort of allow us to map an image of whatever we're looking at. Okay. And the final one, and this one's got really cool implications for mass travel, is maglev. So maglev stands for magnetic levitation, and quite literally it's a train that levitates magnetically above the ground. And this is really important for travel because it basically reduces ground friction. So this will reduce ground friction. And what this allows the train to do is basically travel really, really fast. So I think, yeah, any form of magnetic bullet train uses this, and it allows a train to achieve speeds which it would normally not be able to using traditional rail and wheels. Okay. And it basically just uses the Meissner effect to a much larger degree. The train will generate a magnetic field underneath it, which will then be opposed by the superconducting magnets of the rail track, and you can keep the train above the ground and reduces friction, and basically just travels really, really fast. I think, as far as I understand, the best example of these trains is in Japan, and people have been looking to sort of introduce maglev trains to North America, but the infrastructure necessary would require a lot of money to build. Okay. Alright, so there's some applications of superconductors and electromagnets. And yeah, your assignment for today then is as follows. If you guys have any questions, you guys know how to contact me.